Ever wondered how the number of phases, components, and variables in a system are interconnected in chemistry? Well, to answer that, we introduce the phase rule. It's a principle that provides an insight into the behavior of different systems under varying conditions of temperature and pressure. It's like a map guiding us through the complex terrain of chemical systems. The phase rule, formulated by Josiah Willard Gibbs, is a fundamental tool in the field of physical chemistry. It's not just a theoretical concept, but it's also of practical significance. And here's where it gets interesting for pharmacy students among us. You see, the phase rule plays a crucial role in understanding the stability of pharmaceutical formulations, the design of dosage forms, and the behavior of drug substances under different conditions. To unravel the complexity of the phase rule, we need to delve deeper. So buckle up as we embark on this fascinating journey through the world of phases, components, and variables. The phase rule, often attributed to J. Willard Gibbs, is not as daunting as it may seem. It's simply a principle of thermodynamics that helps us understand the behavior of systems in equilibrium. The basic formula for the phase rule is F equals C minus P plus 2. But what do these letters stand for? Let's break it down. F represents the degrees of freedom, which are the variables that can be independently changed without altering the state of the system. Think of them as the knobs and buttons you can adjust on a stereo system, affecting volume, balance, and so forth without changing the song that's playing. Moving on, C stands for components. In thermodynamics, a component refers to a chemically independent constituent of the system. For instance, in a mixture of water and ethanol, we have two components, water and ethanol. These are independent because they don't chemically react with each other, and their proportions can be varied independently. P, on the other hand, represents phases. A phase is a region of space that is physically and chemically uniform, separated from other regions by a boundary. In simple terms, it's like the different states of matter, solid, liquid, and gas, that a substance can exist in. For instance, in a glass of ice water, we have two phases, the solid ice and the liquid water. So the Gibbs phase rule, F equals C minus P plus 2, tells us how many degrees of freedom we have in a system, given the number of components and phases. It's like a roadmap guiding us through the complex landscape of thermodynamics, helping us understand how different variables interact and influence the state of the system. So with the basics in hand, let's explore some practical applications. Visualize a single component system, water for instance. Water, a simple molecule, H2O, is a perfect example of a one-component system. It's a system where we only have a single chemical species, yet it can exist in three different phases, solid, liquid, and gas. This is where the Gibbs phase rule comes into play. The Gibbs phase rule is a fundamental principle in thermodynamics that gives us a framework to understand the behavior of substances under different conditions of temperature and pressure. It's expressed as F equals sign Cp plus 2, where F is the number of degrees of freedom, C is the number of components, and P is the number of phases. Let's apply this to water. In our one-component system, the number of components, C, is 1, as we only have water. Now, consider a scenario where water coexists as ice, water, and steam. Here the number of phases, P, is 3. Substituting these values into the Gibbs phase rule, we get F equals 1 to 3 plus 2. This simplifies to F equals sign 0, meaning there are no degrees of freedom. This is known as the triple point of water, a unique state where all three phases coexist. Now let's consider another scenario. Water existing solely as a liquid. Here, the number of phases P is 1. Substituting these values into the Gibbs phase rule, we get F equals sign 1, 1 plus 2. This simplifies to F equals sign 2, indicating 2 degrees of freedom, typically temperature and pressure. In this state, we can vary temperature and pressure independently without changing the phase of water. The phase diagram of water, a graphical representation of how the state of water changes with temperature and pressure, is a practical application of the phase rule. It illustrates the regions of stability for the solid, liquid, and gas phases of water, and the points of equilibrium where two or all three phases can coexist. Water, as simple as it may seem, showcases the intricate dance of the phase rule. Understanding these principles not only deepens our appreciation for the complexity of the world around us, but it also sets the stage for exploring more complex systems, which we'll delve into in the next segment. Now, imagine the complexity elevating as we move to 2 and 3 component systems. When we talk about 2 component systems, we're referring to mixtures that contain 2 distinct substances. In these scenarios, the phase rule equation transforms slightly. It becomes F equals sine C, plus P plus 2. Here, F represents the degree of freedom, C is the number of components, and P signifies the number of phases. This formula tells us that the degrees of freedom increase as we add an additional component. So what does this mean in practice? Well, let's consider a simple example: a mixture of water and ethanol. At any given pressure, there are 3 possible phases: liquid, vapor, and a liquid-vapor mix. With 2 components and 3 phases, our phase rule equation tells us there is 1 degree of freedom. This means that we can only change one condition, such as the temperature, without altering the system's equilibrium. Now let's kick it up a notch and venture into 3 component systems. These are mixtures that contain 3 distinct substances. Here, the phase rule becomes F equals sine C, P plus 2, just like with 2 components, but the C in our equation is now 3. Let's take a pharmaceutical example, a mixture of a drug, a filler, and a binder. Depending on the conditions, you might have a solid phase, a liquid phase, or a solid liquid mix. If all 3 phases are present, our phase rule tells us that we have 2 degrees of freedom. This means we can alter 2 conditions, such as temperature and pressure, without disturbing the system's equilibrium. So, as you can see, as we increase the number of components in a system, the degrees of freedom increase, but so does the complexity. We have more variables to play with, but we also have more factors to keep in mind to maintain equilibrium. In the world of chemistry, as the components increase, so does the drama of the phase rule. Let's bring it home to the realm of pharmacy. The phase rule, though a seemingly simple equation, is a powerhouse of practical application in the pharmaceutical world. It's a compass guiding us through the complex maze of drug formulation and stability. Pharmaceuticals are a blend of various components. Each component has its own physical and chemical properties. To ensure a drug's effectiveness, it's crucial to understand how these components interact under different conditions. Here, the phase rule becomes our trusted guide. Consider a case where you're dealing with a drug that's sensitive to temperature changes. The phase rule helps us understand how the drug will behave when the temperature fluctuates. Will it remain stable or will it break down? The phase rule provides us with these answers, ensuring that the drug remains effective and safe under varying conditions. Or think about the formulation of a multi-component drug. The phase rule can predict the compatibility of these components, helping us avoid unwanted reactions that could compromise the drug's effectiveness or safety. In this way, the phase rule helps in the design of stable and effective drug formulations. Moreover, the phase rule is fundamental in the development of controlled-release drug systems. These are systems designed to release the drug at a controlled rate to maintain its therapeutic effect over a prolonged period. The phase rule assists in predicting and controlling the rate of drug release, ensuring the drug's therapeutic effect is maintained. Lastly, the phase rule is also instrumental in quality control. It aids in identifying the conditions under which a drug exhibits optimal stability, which is essential for determining storage and transportation conditions. In summary, the phase rule is a cornerstone in pharmaceutical science. It assists in the development of safe, effective, and stable drug formulations. It guides us in understanding complex systems and predicting their behavior under varying conditions. The phase rule, a simple equation, is a powerful tool in the hands of a pharmacist. So what have we learned today? We've taken a deep dive into the fascinating world of the phase rule, a powerful tool in understanding the behavior of different systems, be it a single component like water or more complex 2 and 3 component systems. Our journey began with an introduction to the Gibbs phase rule, painting a clearer picture of how it helps in predicting the phases of a system. We saw how water as a one-component system exhibits different phases under varying conditions. Moving ahead, we explored even more intricate 2 and 3 component systems, expanding our understanding of the phase rule. But why is this relevant? Well, the significance of the phase rule in pharmacy is immense. It assists in drug formulation and stability, helping to enhance the effectiveness of pharmaceutical products. The phase rule is more than an equation. It's a key to unlock the mysteries of chemical systems. Subscribe for more because you won't find me later.